Dear students, welcome to the course of Mathematical Methods in Physics. I am Dr. Muhammad Ul-Haq, and today we will discuss about. I will introduce you to the complex numbers, and we will formally start the complex variable theory. So these are the. This is the list of topics that we will cover in this course, in this section. And this is a long topic with several subtopics like I have mentioned in the slide. So we will start with complex variables and functions, and then we will go into detail and read about Cauchy-Riemann conditions, Cauchy integral theorem, Cauchy's integral formula, Laurent expansion, singularities, calculus of residues, and we will solve definite integrals in complex of the complex functions. And there are some smaller topics that we will also discuss, which I haven't mentioned here. This part of the course will constitute around about 6 to 8 lectures at least, and you will learn a lot of things related to complex numbers and complex analysis. I briefly mentioned some applications of complex theory. So with the help of complex theory, we can solve two-dimensional Laplace equation with the help of conformal mapping. This is also a subtopic of complex analysis. We will discuss it in a full lecture, what is conformal mapping. Then we will discuss, or we may not discuss, but we find uses of complex analysis in quantum mechanics. You will get a course of quantum mechanics hopefully in 6th semester, I think, and you might also study series expansions with analytic continuation. This is also a topic of quantum mechanics and some other fields, but it's not like a standalone topic. But you have to use complex expansions of certain functions. And another is transformation between special functions. Okay, we will not go into detail, but we can do with the help of. And a big part of this section, this complex analysis, is contour integrals. So in contour integrals, we do some integrations, we have some singularities, and we have some formulas to work with this contour integrals. So this would be a somehow longer topic in this complex analysis, and we may not discuss maybe these last three, although they are part of this contour integral thing. But for part A, B, and C, for sure we will discuss, and we will solve some problems. Other more general things in physics that are related to complex analysis are a refraction index. So a refractive index is what you call transposed or divided, or whatever you call it, into two parts, real and imaginary parts. This is also subtopic of complex analysis. And energy, and there is something called like dielectric constant. So it also has two parts, real part and an imaginary part. So these are the applications of complex theory. So as you progress in physics, going to higher semesters, you will use complex analysis more and more, or more often. And this is an extremely useful theory, and you will get the actual taste of this theory later in the semester, or later in the yes, physics, but you should know complex analysis in much more clear detail. So today we will start from really basic stuff. So as I mentioned here on the slide, that you might have heard about complex numbers, but we will start from the beginning. So we start with this quadratic equation, this az square plus bz plus c equals 0. This is a quadratic equation because it contains the squared power of the variable. The variable this is a function of z, so it contains the second power of z. So az square plus bz plus c equals 0 is a, b and c are constants. A, B and C are constants, some numbers, and you know from elementary algebra that this equation can be its roots or its the values of the variable z can be found out with the help of quadratic formula, and the quadratic formula is given by is given in terms of these constant a, b and c, that is minus b plus minus b square minus 4ac whole square root whole divided by 2a. So this is this formula you know by heart from your metric and FSC classes. Nothing new about that. And we will discuss a particular case of this formula. So you see here inside the formula we have a term like this, that is square root of b square minus 4ac. So this is a really really interesting term, and it can be funny sometimes that okay, you know that if b square is greater than 4ac, then I write it here explicitly, if b square is greater than 4ac, this number inside this square root is a positive number. So you see that b square minus 4ac is greater than 0, and then everything is fine. I mean, you get the values and everything goes very well. There is nothing unusual in that. But there can be certain equations, these quadratic equations, where this value b square minus 4ac is negative. So the case is that you have b square is smaller than 4ac, and then you have b square minus 4ac less than 0. And this is a very interesting situation, because in that case you have a negative sign inside the square root. So you have square root and minus 1 times some constant term, some number, and you when you write this, so you have from elementary algebra you have everything for positive values inside square root, but you have nothing which deals with the square root of minus 1. So to deal with this kind of situation, so mathematicians came across this interesting number, what you call iota. So they say, okay, if we have anywhere square root of minus 1, so we will call it iota. I kind of symbol we use for that. So we use iota whenever we have this kind of funny situation of minus 1 inside the square root, because it cannot be something related to natural numbers. So we have to invent some new kind of terminology for that, and that terminology we say that these numbers are now complex numbers. So I go into details of these complex numbers, but I just give you some properties that okay, if I is square root of minus 1, then what is I multiplied by another I or iota? So that would be minus 1. Minus 1 square root times minus 1 square root. So that would be minus 1, just minus 1. And you can write any number just like it is mentioned here, that under root or square root of minus 16 equals. So you take square root of 16, and then for minus 1 part, so you write it like this, so that is minus 16, that would be equal to 16 times minus 1. So you get square root of 16 as 4, and for minus 1 under root you write just iota. And okay, so you can write several things with the help of this. As an example, you see this equation, this quadratic equation given here, z square minus 2z plus 2. So here if you use quadratic formula, you will get in the square root and 4 minus 8, so you get minus 4 inside. So if you solve this, you get at the end of the day this kind of number, 1 plus minus iota. And the funny thing is, okay, we call this complex number 1 plus or minus iota. So you see that it has two parts. So there is one part that is like just like a real number, and you have a second part that contains this iota part. So now we constitute something, we call it complex number theory. So we define what is a complex number. A complex number any number that can be written as some constant a plus iota. So I should mention here it should not be read as I, but it should be as iota. So any number which can be written as where a and b are constants is called as a complex number. So it can be usually of this shape, as I mentioned here, but it can be any number. So that is interesting. So for example, I say that 5 is a complex number. Okay, so you usually denote this complex number with in notations like z equals a plus iota b. So if I write 5 and I say it's a complex number, so it is also true. So you can think, how is it true? Because 5 can also be written in this shape, z equals a plus iota b. The difference is that when you write 5 as in the form of a plus iota b, so what you do, you write 5 equals 5 plus 0 iota. So we say that it has two parts, one is a real part and one is imaginary part, and for only the number 5, the imaginary part is 0. We call this the part of the complex number that contains iota is called the imaginary part. So we say that imaginary part of 5 is equal to 0. And so any number can be written as a complex number. So every natural number is a complex number. In addition to pure complex numbers, like which can be exactly written as just like 2 plus 3 iota, which have distinct real parts or non-zero real parts and non-zero imaginary parts. Or it can have there can also be a case when you have something with 0 real part and some imaginary part. For example, if we write 5 iota, so in this case it can be written as 0 plus 5 iota. So this is also a complex number. So you see that the real part of this complex number 5 iota is 0. Okay, so that is interesting. Moreover, you should always remember that the real and imaginary parts, the real and imaginary parts of a complex number are always real numbers. What does that mean? So in have you seen that this a plus iota b, so a and b, they are not imaginary numbers. So if you put iota, then the whole thing becomes a complex number, but a and b separately are real numbers always. So if this is the case, so in normal geometry, what we do, we plot pairs of numbers. So if we have a point in two-dimensional plane, so this is a plane, as I mentioned, it's written on your screen, that we are defining now a complex plane kind of thing. And you should remember that whenever you plot on a normal plane, so we have a normal plane that is non-complex plane. So plane is anything that has two dimensions, x and y. We call this x and we call this y. And if we want to locate a point on this plane, so we have to give it two coordinates. Say this is a point P on this plane and we have to locate it. So we have to draw a line on x-axis and there should be okay. The marking is like 1, 2 and 3 here, and on y-axis it is say 1, 2, 3, 4 and 5. So this point is we write in the form of a ordered pair, so that is 3, 5, and 3, 5 stands for this is the x component and this is the y component. 3, 5. This is the normal plane, not the complex plane. Any point on a two-dimension on a two-dimensional surface, we can write it like that. So in the same fashion, we define a complex plane. So as we have seen here, that a complex number is written as either x plus iota y or a plus iota b. So whenever we have a number like this, a plus iota b or x plus iota y, however you like it, so we can also write it in the form of an ordered pair, a, b, like two real numbers. But there should be a distinction that now the plane that we will use, it would not be a normal plane, it would be a complex plane. First thing. And so in case of a normal plane, we had two real axes, x real axis and y real axis here. But in case of complex plane, so we have a real axis here and an imaginary axis here. So we call this imaginary, so it has nothing to do with your imagination, but this is like a terminology kind of thing, that now everything that has this shape A or X, that will come on the real axis, and whatever is related to iota part, it will go along y axis. So any number x plus iota y here, as we have shown, it is mentioned here, x plus iota y, and any number like that 5 plus 3 iota, for example, or ordered pair 5, 3 is mentioned here. So this is like on x-axis there are 5 points and on y-axis there are 3 points. So I hope you get what I wanted to say, that any complex number in two-dimensional plane can be shown as an ordered pair on a complex plane, any number. Okay, so the complex plane one representation as I have shown it to you already on this graph, that is you write ordered pair x-axis y-axis, but there is another way that you can transform this kind of representation into uh, into uh, into polar coordinates. You know the polar coordinates, so you have you go from xy to, so you transform from xy to another set of coordinates, that is r theta coordinates. So what is the difference between these two? So this is just a transformation. So for that you already know, but I somehow repeat for you that you should take into consideration this triangle. So this is the length on in the x direction, this is the length in the y direction, and you have an angle theta between this r vector. R vector is basically connecting the point and the zero of the axis here. This is the zero of the axis, and this r is a vector that connects between the point P and this zero. So you have to change from xy to r theta. So if you see now that in a right triangle, so you know what is a right triangle that has one angle of 90 degrees. So this is the angle of 90 degrees, and the angle corresponding to is the opposite of this 90 degree, we call this theta. And so if you see now, so x, from your knowledge of trigonometry, so x is now equal to r cosine of theta, and y equals r sine of theta. So this is pretty straightforward, you know, from your elementary knowledge, that x is equal to r cos theta and y is equal to r sine theta. So if you now want to change this x plus iota y, so you just have to plug in these values. You say, okay, you are moving from xy to cos theta, so you say that x is equal to r cos theta and y is equal to r sine theta. That's it. And then you take r common, and then your complex number in polar form is written as r cosine theta plus iota sine of theta. So you see here, x plus iota y is transformed as r cosine of theta plus iota sine of theta. It's simple as that. And now from complex analysis, you can always write e to the power iota theta as cosine of theta plus iota sine of theta. This is the exponential form of the complex number. So you just replace from here this r cos theta plus r sine theta into r e to the power iota theta. You know it beforehand, it's just a repetition of things. So the complex number that was written as x plus iota y, if you someone says, okay, we have some values of a complex number in a Cartesian geometry, x and y, you convert it into a polar form. So what you do, you just use this formula. Now you have to determine theta from your geometry, and then all is set. So just you have to determine r theta, and then your complex form of that particular complex number can be easily found using this r e to the power iota theta, and you call this polar form. And what we used to call this other form, x plus iota y shape, we call this Cartesian form. So we call this Cartesian form. Okay, so we have another example lined up for this. So here you are given a complex number 1 plus uh, under root 3 or square root of 3. So you have given in a Cartesian form z equals 1 plus square root of 3 iota, or in the form of ordered number you can write it 1 and square root of 3. So this is your x and this is the y. You now have to convert this into polar form. So to convert it to polar form, you have to take into account this geometry. So first of all, you need to determine what is r, this thing, and what is this angle theta. So in this example it's already mentioned, but you have to do it on your own without looking elsewhere. So how would you do that? So from simple trigonometric considerations, so the magnitude of z, we call this thing as r. You should remember now what is r. R is the magnitude of that. Magnitude of z is the actual length of that r vector. And how you determine that z magnitude? So that if z is x plus iota y or a plus iota b, so your z mod is square root of x square plus y square. So if you now compare it with this equation, you get that in our case r z mod in this case would be 1 squared plus square root of 3 squared. So that would be 1 plus 3 and that would be 2. So that's how you mention r equal to here. This is the length of this vector in polar coordinates. And if you now want to determine theta, so you should use again some geometry, trigonometry, what you call it. So I should leave it on you how you determine this theta. I think you are familiar with this kind of terminology, but still I wish that you should recall this kind of trigonometry to determine this angle. So you are given r, you are given x and y, and if you recall that kind of there would be a formula related to tan of theta, and if you now plug in the value, tan theta would be can be written in terms of these x and y. You should tell me what are those x and y, how they should be should be written as. You should recall what is tan of theta, and if you can recall that, then it's easy. Then you will get theta by taking tan inverse of that thing, and then if you can get theta, then x would be equal to r cosine of theta, and from there you just put the values to cos of that angle theta, and that would be converted into polar coordinates, and that is it. So actually you just need to write z equals r e to the power iota theta. So you don't need to go to this. You just we have already determined r, and if you determine now theta, so it would be easy to write this complex number into in this shape. Z is equal to r e to the power iota theta. So that is relatively easy stuff for you. Okay. So I just stop the lectures here, and I don't want to overburden you today. So this was a brief introduction, and from next lecture onwards, we will go into more detail